So, hi everyone, my name is Piyumi. I'm a second year PhD student from Faculty of IT, Monash University, Australia. Today I'm going to talk about our approach to model joint distributions of backbone and sidechain dihedral angles of amino acids in proteins. So, so I have moved to this slide, sorry about that. So, proteins are composed of linear chains of amino acids that fold into complex 3D shapes. This 3D shape or 3D structure of a protein is determined by individual amino acid conformations. And more precisely, these conformations are determined by rotational freedom along the bonds. And we can quantify this rotational freedom in terms of dihedral angles. Simply, a dihedral angle is an angle between two intersecting planes. For amino acids in proteins, these dihedral angles are defined along the backbone as phi psi omega and defined along the side chain as chi1 to chi d, depending on the amino acid being considered. And here, each dihedral angle falls in the range negative 180 degrees to positive 180 degrees. And by using these dihedral angles, we can express the conformation of any amino acid as a d-dimensional vector. And one thing to note here is that in this representation, mostly omega angle is not considered because of its restricted rotation along the peptide bond. And if we consider models of dihedral angle distributions, they play a pivotal role in studies involving protein structures because these models are widely used in experimental structure determination, validation, protein design, likewise. And if we consider current models and current approaches, they have multiple limitations. For example, they model backbone and sidechain dihedral angles separately, and they tend to discretize the dihedral angle space into coarse-angular bins. And when modeling backbone dihedral angles, they tend to use a general model without using an amino acid-specific model. And also, current models are complex and they attempt to overfit the data. And in order to address these limitations, we introduce a new set of statistical models that model the joint distribution of phi, psi, and chi dihedral angles. And shortly, we call these models physical. Physical models are based on a minimum message length information theoretic framework. And at physical, we model the joint distribution of backbone and sidechain dihedral angles. And for this purpose, we infer statistical mixture models in an unsupervised environment and in the continuous space of these dihedral angles. And here, all these mixture models are specific to individual amino acid so that we don't rely on an general model. And most importantly, these mixture models trades off model complexity with model fit in order to avoid overfitting. So let's dive into the details of physical implementation. And at physical, the conformation of any amino acid containing d-dihedral angles of phi psi chi is treated as a point on a multidimensional torus. So to your left, you can see the conventional scatter plot of phi psi dihedral angles of alanine amino acid. So we can map this distribution to the toroidal space as follows, as a distribution on a 2 torus in the 3-dimensional space. And similarly, we can map the distribution for the remaining rest of the amino acids as well. But for the ones which have more degrees of freedom, more than 2 degrees of freedom, their corresponding distribution lies in a multidimensional torus that actually cannot be represented in the 3-dimensional space as previously. So from these distributions, you can see that the overall population is a mixture of subpopulations. And due to this fact, we model these distributions mathematically as statistical mixture models. Simply, a mixture model is a weighted sum of probability distributions where these weights should add up to 1. Let's say we have a mixture model represented by M and having parameter lambda. And here this weighted summation can be represented as follows. The summation is taken over the number of components of the mixture model. W corresponds to weights of components, and F theta is the probability density function or probability distribution that we consider in the mixture model. And one important thing to note is that in an inference exercise, we don't have any prior information or prior knowledge of these parameter values, the number of components, component weights, and component parameters. And because of that, we have to resolve these values as a part of the inference. And going back, so in physical, this f theta, the probability density function, takes the following form as a product of von Mises distributions. So with this representation, our goal was to find best statistical mixture models that explain the joint distribution of dihedral angles and in an unsupervised environment. And in order to do that, we employ a Bayesian information theoretic framework, minimum message length. To give you a brief introduction into minimum message length, MML assumes an imaginary transmission between a sender and a receiver. The sender needs to send data, represented as D here, to a receiver, and this is done as a two-part message, where the first part of the message contains the model, represented as M here, and second part of the message contains the data given the model. And during this transmission, the receiver should be able to recover the original data losslessly, and sender should send the data in such a way to facilitate this lossless recovery. And this is achieved by combining the Bayes theorem with Shannon's information theory. So from the product rule, we can state the joint probability of a model and data as product of probability of the model and probability of data given the model. And from Shannon's information theory, it quantifies the optimal message length, which is required to state an event E in terms of its probability. And let's apply the Shannon's information theory on top of the product rule. And from that, we get the optimal message length, which is required to send this data as a two-part message. Here, the first part of the message contains the model, and second part of the message contains the message length required to send data given the model. And here, this first part, which contains the message length of the model, quantifies the complexity of the model, and second part quantifies the fit of the model, or how well this model explains this data. And under MML framework, the best model for any observed data D is the one minimizing this two-part message length. So under this MML framework, our goal was to find statistical mixture models given d-dimensional dihedral angle data that minimizes this two-part message length. Sorry. So to achieve this goal, let's explore the message length of a mixture model. For a mixture model, the first part deals with sending the mixture model or sending mixture parameters. And here, this first part can be stated as summation of three message length terms: the message length required to send the number of components, component weights, and component parameters. And second part is simply the message length required to send data given the mixture model, and arithmetically, we can represent this as the negative log likelihood over the observed data. So with that, we can express the total message length of a mixture model as follows. And here, the first part quantifies the complexity of the mixture model, and second part quantifies the fit of the mixture model. So with this message length representation, which is used as our objective function, we search for the optimal mixture model that minimizes this two-part message length, and this is done in an unsupervised environment. And in order to do that, we employ a incremental search strategy that start with a single component and perform a well-defined set of operations called split, merge, and delete. So here, in order to understand the functional flow of this search algorithm, let's assume that we are at an intermediate stage of this algorithm. And at this stage, we have a k component mixture. And initially, this k was equal to 1. And here, for each of these k components, we execute these three operations called split, merge, and delete. During split operation, we split each k component independently in order to add new components to the mixture model. And after that, we execute an expectation maximization algorithm in order to determine optimal component weights and component parameters. And by doing that, this method allows us to find the optimal mixture model resulting from the split operation. During merge operation, we merge each K component with its closest component in terms of KL divergence, and similarly execute an EM algorithm in order to determine optimal component weights and component parameters. And similarly, this method allows us to find the best mixture model resulting from merge operation. And during delete, similarly, we remove each K component from the mixture model independently and then execute the EM algorithm. And similarly, this method allows us to find the best mixture model resulting from delete operation. So on completion of these three operations, now we have three mixture models, which are the best split, best merge, and best delete mixture models. And after that, we compare these three models with each other, and we only select the one having the minimum message length. Finally, we compare the message length of this new mixture model with the starting mixture model, the one we started with. And if there's any improvement in the message length, we continue the search process. And if there aren't any improvement, the search stops. And the starting mixture model at that iteration is treated as the inferred mixture model. So with this search algorithm, it allows us to find the optimal mixture model, which is able to explain the joint distribution of dihedral angles. So as there aren't any previous work on modeling dihedral angles on the joint space, we compare the accuracy of our physical mixture models with the current state of the art for modeling and sampling sidechain conformations. And for this purpose, we used Dunbrack's backbone-dependent Rotamer library. Dunbrack's Rotamer library provides sidechain conformations conditioned on the backbone. And for this purpose, they use a 10 cross 10 degree discrete grid for backbone dihedral angles. And for most amino acids, they used a three-way discretization for sidechain dihedral angles. And during these comparisons, we did the comparisons in a quantitative as well as a qualitative manner. And during quantitative comparison, we compared the complexity and fit between these two models, the physical mixture model and the Dunbrack's Rotamer library. And during qualitative analysis, we analyzed the fidelity of the inferred models. So this table shows a quantitative comparison between MML inferred models and Dunbrack's Rotamer library in terms of message length across all the amino acids when encoding a non-redundant protein dataset. Let's take any amino acid for comparison. In this case, let's take lysine. Lysine has 6 degrees of freedom from 5 psi in the backbone and 4 sidechain dihedral angles. And for lysine, MML inferred a mixture model with 266 components. And across these components, there are around 3,000 component parameters. On the Dunbrack side, as it is a backbone-dependent Rotamer library, the backbone space is discretized over around 1,000 bins. And for each bin, they have their own set of components or models. And if we consider overall this 5 psi grid, across all these 5 psi grid, there are around 100,000 components. And across these 100,000 components, there are around 1 million component parameters. And we can compare the complexity between these two models by using the first part of the message. And for the MML case, this takes around 10,000 bits to state the complexity of the mixture model. And for the Dunbrack's case, this takes around 14 million bits. And after this, we can ask the question how well these two statistical models explain the observed data. And this is captured by the second part of the message. So for the MML case, this is around 22 million bits, while for the Dunbrack's case, this is around 35 million bits. Or in other words, from the physical mixture model, this is around 37% more lossless compression, which is provided. And zooming back to the original table, so we have done this comparison across all the amino acids. And overall, we were able to show that the physical mixture models outperform the Dunbrack's Rotamer library in terms of model complexity by 3 orders of magnitude. And in terms of fit, on average, physical mixture models are able to provide 20% or more lossless compression. And after this quantitative comparison, let's consider a qualitative point of view. Here, this illustration shows sidechain conformations projected into their individual dihedral angle space for a subset of amino acids. So if you want to look into these qualitative comparisons across all the amino acids, you are welcome to read our paper. And similarly here, let's take any amino acid. And for this case, let's take methionine. Methionine have 3 sidechain dihedral angles from chi1 to chi3. And in this illustration, the empirical distribution is shown from the yellow color. And here, for the Dunn-Brax distribution and for the physical distribution, we have randomly sampled data and to create these plots. So the distribution from the physical mixture model is shown from the blue color, and the distribution from the Dunn-Brax rotamer library is shown in the red color. And here we can notice that the physical mixture model have a more tighter distribution to the empirical data compared to the Dunn-Brax model. And overall, this is true across most of the amino acids. And moving on to the next slide. So here we show the combined view across multiple dihedral angles for 2 amino acids, methionine and glutamine. And similarly, here also to create these plots, we have randomly sampled data from the mixture model and Dunn-Brax rotamer library. So to your left, we show the distribution from the empirical data, and in the middle, distribution from the random samples from the physical mixture model is compared against the distribution from the Dunn-Brax library. And again, it confirms what we saw previously, that the physical mixture model has a more closer distribution to the empirical data. So with this work, we introduce physical mixture models that model the conformation of amino acids in proteins. Compared to existing models, physical mixture models provide a more accurate representation of the joint of the dihedral angle space. And most importantly, these models are inferred unsupervised and supports more applications as we model the joint distribution of dihedral angles. In order to facilitate these applications, we have made available physical sampler that enables you to sample joint conformations as well as sidechain conformations conditioned on the backbone. And finally, stay tuned for physical checkup that utilizes these mixture models in order to do protein structure validation. And finally, this concludes my presentation. Thank you very much for your attention.
Great presentation, second year PhD student, amazing. One question here.
Thank you for your presentation. I have a very naive question. You said it's lossless, but it seems to me these mixture models seems to me they are lossy because you find the optimal parameters and then you want to reconstruct it, and it's not deterministic to go back and find the same distribution of the dihedral angles. Why you are saying it's lossless?
Yeah, so if you consider MML paradigm, so it is actually a lossless data compression framework, that meaning that when we send the data to a receiver, we should ensure that we send all the details associated with our model so that in the receiver's end that they can decode the data and recover the original data losslessly. And from the Shannon's information theory, so MML is based on Shannon's information theory and also the Bayes theorem. And from the Shannon's information theory, it tells that the optimal message length that is required to send an event E losslessly can be expressed in terms of its probability. So the framework is itself.
This I agree
yeah.
with that. But the expectation maximization process, we can talk on the possible.
Sure.
Very nice work to characterize the entropy. So my question is that here, because the interaction, so the distribution will be more ordered, so message length will be shorter. So have you tried to set up the reference state which allows the uniform distribution for any dihedral angle? So that will correspond to the most disordered state. So if you compare it with that reference state, you will be able to characterize the so-called conformation entropy change. And I want to say, have your comment on that?
So is that the question that we have compared with the uniform distribution for the? Yes, absolutely. So we consider that as a null hypothesis. Oh, yep, yes, we have done that. And actually in our paper, we have included results for that as well. And I have removed that columns in this presentation because it was too large to fit in here. Yeah.